Close your eyes for a moment. Not all the way, not yet. Just enough to let the edges of the room blur a little. Let your shoulders drop. Feel the weight of your body sinking into the mattress, the quiet pressure of the pillow beneath your head. The day is done. Whatever it held, the noise of it, the pace of it, it belongs to another version of you now. The version that will wake up tomorrow, rested. Right now, you have nowhere to be and nothing to do. Let your breathing slow, in through the nose and out. There is something particularly beautiful about this hour, the in-between time when the world outside goes quiet and the mind begins to drift at its own unhurried pace, like a leaf floating down a river with no particular destination. Tonight, we are going somewhere very old. Older than any city, older than any mountain range you have ever seen. We are going back 50 million years to the edge of a warm, shallow sea where the air smells of salt and damp earth, where enormous ferns brush against the shoreline and the water is glassy and copper-colored in the late afternoon light. And standing at the edge of it, watching the water, drawn to it in a way it cannot quite understand, is an animal that looks to our eyes something like a wolf. It does not know as it wades into the shallows that its descendants will one day be the largest creatures ever to have lived on this planet. It does not know anything about what is coming. It simply steps into the water. It lowers its long snout to the surface. And a story begins that will take 50 million years to tell. The story of whales is, at its heart, a story about going home. And like most journeys home, it begins somewhere unexpected. Cast your mind back to the early Eocene, roughly 50 to 53 million years ago. The planet is warm, nearly 10 degrees warmer on average than it is today. There are no polar ice caps. The continents are in different positions, drifting their slow way toward the familiar shapes we now recognize from maps and globes. What is now Pakistan, what is now northern India, sits on the edge of a vast ancient ocean called the Tethys Sea, a warm, sunlit, shallow body of water full of fish, full of life, framed by coastlines of low tropical forest and river delta. And living along those coastlines is an animal that paleontologists have named Pachycetus. The name means Pakistan whale, and it was found, its fragmentary skull first pulled from the red-brown rock of the Kuldana Formation west of modern-day Islamabad in 1981 by scientists who immediately noticed something remarkable about its inner ear, something that linked it, unmistakably, to whales. But set that knowledge aside for a moment and just imagine the animal itself. Pachycetus is roughly the size and build of a wolf, though perhaps a little longer in body, between 1 and 2 meters from snout to tail. It has 4 legs. It has a long, flexible tail. It has a narrow, pointed snout full of sharp teeth that speak of a meat eater, a fish catcher, a hunter. It probably has fur, or at least a short, sparse coat. The way its closest surviving relative, the hippopotamus, has only a scattering of coarse hair. Its eyes sit close together on the top of its skull, a little like a crocodile's, positioned to look upward through shallow water to watch for prey swimming above while its body is submerged below. It lives along the margins of rivers and lakes and the coastal shallows of that ancient Tethys Sea. It wades in, it catches fish, it comes back out onto the warm, flat mud banks to rest and eat. its belly low to the ground, its legs sprawling a little to either side. In behavior, perhaps, it is something like a modern otter or a small crocodilian, an animal that is equally at home wet or dry, that does not need to choose between worlds. What makes it remarkable is not anything you could see from the outside. What makes it remarkable is a small, dense structure inside its skull, the auditory bulla, the bony housing of the inner ear. In almost all mammals, this bone is a certain shape, a certain density, but in Pachycetus, it is thick and solid in a very particular way, a condition called pachyosteosclerosis. And that exact condition appears in exactly one other group of animals across all of evolutionary history: whales, modern whales, the blue whale, the humpback, the sperm whale, the orca. All of them carry that same inner ear structure, and Pachycetus had it too. This is how evolution leaves its signature, not in grand announcements, but in small, dense bones tucked inside a skull, in the weight of an ankle joint, in the chemical composition of a tooth. Scientists can also read the oxygen isotopes locked into Pachycetus's bones, isotopes that record like a diary what water the animal drank as its skeleton formed. And those records show a creature drinking both fresh water and salt water, an animal already testing the boundaries, already leaning toward the sea. There is also the matter of the ankle bone. In 2001, a more complete skeleton of Pachycetus was found, and it revealed something extraordinary: an astragalus, the central ankle bone, with a distinctive double pulley shape found only in artiodactyls, the even-toed hoofed mammals, pigs, deer, giraffes, cows, and hippopotamuses. Pachycetus, this early whale, this fish catcher with the dense inner ear, had the ankle bone of a hoofed animal, and because that is precisely what its ancestors were. The whales did not come from nowhere. They came from the ungulates, from the hoofed mammals of the ancient world, and Pachycetus stands at the hinge point, 1 foot in the old world, 1 foot, or rather one small wet paw, in the new. The transformation from land mammal to ocean giant did not happen overnight. It did not happen in a lifetime or 100 lifetimes. It happened slowly over millions of years through countless generations, one small shift at a time, the way a river finds its way through rock, not by force but by persistence, by patience, by the endless accumulation of small movements. About 5 million years after Pachycetus padded along its muddy riverbanks, a new creature appears in the fossil record of the same region. Its name is Ambulocetus natans, and that name is almost too perfect. It means the walking whale that swims. Paleontologist Hans Thewissen found its bones in the Kalachita Hills of Pakistan in 1992, and when the description was published in 1994, it immediately became one of the most celebrated transitional fossils in the history of paleontology. Ambulocetus is considerably larger than Pachycetus. At roughly 3 to 4 meters long and weighing around 180 kilograms, it is closer in bulk to a large sea lion than a wolf. Its legs are still functional. They are present, they are sturdy, they have large paddle-like feet, but they are already beginning to change in the direction of something more aquatic. The limbs splay wide from the body. The animal could come onto land, but it moved there with the slow, effortful heave of a creature that is no longer entirely comfortable in the open air. On land, it likely moved much the way a modern sea lion does, chest low, forelimbs braced against the ground, pushing itself forward with an ungainly rocking gait. In water, though, it was something else, something that, if you could watch it from below, through the warm green light of that ancient coastal estuary, you might almost recognize. Ambulocetus swam by, flexing its spine up and down, undulating its body in powerful waves, driving itself forward with its large hind feet. It swam the way a modern otter swims, the way a whale swims, not side to side like a fish, but up and down, the spinal motion of a land mammal translated into a fluid rhythmic propulsion. The same motion you see in a dog running, that wave passing through the backbone from head to haunch, becomes, in the water, something beautiful. Its eyes were still on top of the head, oriented slightly upward, the ambush hunter's eyes of an animal that lurked in shallow water and waited. It had large, powerful jaws and tall, sharp teeth. It ate fish, and perhaps other animals that came close to the water's edge. The oxygen isotopes in Ambulocetus's bones tell us it drank both fresh and salt water, which fits the picture of an animal living in the brackish reaches of an estuary, where rivers met the sea. The climate around it, the hot Eocene greenhouse, with its tropical forests and warm coastal shallows, must have offered an abundance of food just below the water's surface. Generation by generation, the descendants of these animals found more of what they needed in the water and less reason to come back out. Then comes Rodhocetus, from roughly 47 to 46 million years ago, and the shift has accelerated further. Rodhocetus has a deeper, narrower chest, built for streamlined swimming. Its lumbar vertebrae, the bones of the lower back, are taller and stronger, evidence of powerful muscles running along the tail and lower body to drive swimming. Its front limbs are already smaller relative to its body, less useful for walking and more configured for steering. It can still move on land in a limited way, but a balance is tilting decisively. The ocean is winning. What you are watching across these millions of years is not a single decision. There is no moment when one of these creatures chose the deep over the land. It is a gradient, a slow drift. The animals that were slightly better at fishing survived slightly better and had slightly more offspring. The animals whose ears worked a little more clearly underwater found prey a little more effectively. The ones whose bodies were fractionally more streamlined could dive a little deeper, stay down a little longer, come up a little more easily. Over enough generations, fractional advantages become transformations. The nostrils, which in Pocketatus sat at the tip of the snout the way they do in a dog, begin to migrate. In Ambulocetus, they are a little further back. In Rodhocetus, further back still. The skeleton documents this movement, nostril by nostril, generation by generation, across millions of years, until one day, tens of millions of years from now, those nostrils have arrived at the top of the skull, where they will become a blowhole, a single breath taken in one explosive exhale at the surface of the open ocean before the body rolls back down into the dark. By about 41 million years ago, the process has produced something that could only be described as a whale. Not entirely like the whales we know today, but undeniably aquatic, undeniably at home in open water in a way that nothing before it has been. This is Basilosaurus, and it is spectacular. The name, unfortunately, means king lizard, because when the first fossils were found in the American South in the early 1800s, scientists looked at the great coils of vertebrae and assumed they belonged to a reptile. Only later was the mistake corrected, but the original name stuck, as taxonomy sometimes insists on keeping its errors. Basilosaurus is not a lizard, it is a whale, one of the first fully aquatic whales. It is enormous. The larger of the two confirmed species, Basilosaurus setoides, could reach 15 to 18 meters in length, longer than a school bus, long as a shipping container. But it is not the length alone that catches the mind. It is the shape. Basilosaurus is extraordinarily elongated, its trunk vertebrae stretched into long, almost cylindrical shapes that give the animal an eel-like appearance when viewed from a distance. Its body undulates through the water in long, slow waves. It has 4 limbs that have already become recognizable flippers, broad, paddle-shaped, used for steering. Its tail, long and powerful, almost certainly ended in horizontal flukes, the same horizontal flukes you see slipping beneath the water when a modern humpback begins its dive. And then there are the hind legs. Basilosaurus has hind legs, small ones, tucked beneath the body, not connected to the backbone, not capable of bearing weight, not useful for walking in any way that would have made sense on land. The hips and pelvis in earlier relatives had been firmly anchored to the spine, built to carry the animal's weight against gravity. In Basilosaurus, that connection has been severed. The pelvis floats free. The tiny femur, the tibia, the ankle bones and toes, all still there, all still present, but reduced to something vestigial, something the body has not yet fully let go of. Paleontologists believe these small limbs may have served as guides during mating, bracing points for the long, flexible bodies to hold position. The land was 50 million years in the past, but its signature was still written in these small bones tucked inside a great marine predator. Fossils of Basilosaurus from Wadi al-Hitan, the Valley of Whales, in the Egyptian desert, paint an extraordinarily vivid picture. That desert was, in the Eocene, a warm tropical sea, the floor of the ancient Tethys. And when you walk among the exposed skeletons there, hundreds of them lying in the sand where the water retreated, you are walking across what was once the bottom of that sea. Basilosaurus hunted here. It fed on fish, on sharks, and on smaller whales. Bite marks on the skulls of juvenile Dorudon, a smaller dolphin-like contemporary, match the teeth of Basilosaurus, and inside some Basilosaurus specimens, the preserved contents of the stomach include the bones of fish, turtles, and other marine mammals. Basilosaurus was the apex predator of its world. Around 34 million years ago, the climate shifted. The warm Eocene greenhouse gave way to cooler conditions. The Tethys Sea retreated. The Archaeocetes, those ancient whales, mostly disappeared. But from within their lineage, 2 new groups had already begun to branch off, and those groups would inherit the oceans. One group evolved a remarkable new way of eating. Instead of teeth, they grew long plates of baleen, keratin filters hanging from the upper jaw, which allowed them to take enormous gulps of water and sieve out clouds of small prey. These are the mysticetes, the baleen whales, the group that includes the blue whale, the humpback, the fin whale, and the right whale. The other group kept their teeth, but developed an astonishing new sense: echolocation. These are the odontocetes, the toothed whales, the dolphins, the sperm whales, the orcas, the beaked whales. The fatty melon in the forehead of a dolphin is not just an anatomical feature. It is a sophisticated acoustic lens, focusing outgoing clicks into a narrow beam of sound that bounces off prey in the dark water and returns as an echo to the jaw, where fat pads conduct the vibration to the inner ear. A living sonar, refined over 30 million years. Both groups carry, somewhere inside their bodies, the remnant of hind limbs that no longer exist. Deep within the flesh of a living blue whale, if you looked, you would find small bones, a tiny pelvis, sometimes a femur, that have no function in any mechanical sense. They are a letter sent from 50 million years ago, still arriving. And now we arrive at the deepest water. Now we have come to the blue whale itself, Balanoptera musculus, the end point of that 50 million year journey, and the most physically extraordinary animal that has ever lived on this planet. The blue whale can grow to 30 meters in length. Its weight can reach 150 tons or more. In terms of sheer mass, it is larger than any dinosaur, larger than anything else the fossil record has ever produced. An African elephant, the largest land animal alive today, weighs about 4.5 tons. A blue whale outweighs one by more than 30 times. It is a number that resists easy comprehension, but the number that tends to stop people isn't the length or the weight, it is the heart. Inside the chest of a blue whale beats a heart that weighs somewhere in the region of 400 pounds, roughly the weight of a large motorcycle. It is roughly the size of a small golf cart or perhaps a compact piano. 5 feet tall, 5 feet wide, its walls thick with layered muscle and collagen scaffolding that distributes the mechanical stress of each beat along helical lines, the way the grain runs through a ship's wooden hull. 4 chambers beating in their slow ancient rhythm. On average at the surface, the heart of a blue whale beats somewhere between 8 and 37 times per minute, already slow compared to our own 60 to 100. But during a deep dive, during the long, breathless descent to feed on clouds of krill, that rate can fall to as few as 2 beats per minute. 2 beats per minute. Let that settle in. Your own heart, right now as you lie here, is likely beating somewhere between 50 and 80 times each minute. The blue whale's heart, at its most resting, beats roughly once every 30 seconds. A long pause, and then the slow, deep thump. A long pause, and then again. It is a sound that, in the right conditions, can be heard from 2 miles away through the water. A low, resonant percussion that carries through the ocean the way a church bell carries through winter air. The aorta, the main vessel leaving that great heart, is large enough to fit a human head inside it. The blood it propels is approximately 10 tons of it, cycling continuously through a body that, from blowhole to fluke tip, is the length of 2 city buses end to end. The heart pumps roughly 60 gallons of blood with each beat, a bathtub full of blood released in one slow, powerful contraction, and then the pause, the elastic walls of the aorta continuing to squeeze gently in the interval, smoothing the flow, keeping the pressure even through the long wait between beats. And then there is the sound, not the sound of the heart, though that too, but the sound that comes from the throat, or rather from the complex system of air sacs and vibrating structures near the blowhole, because whales have no vocal cords in the way we do. The sound that emerges from a blue whale is almost beyond description in human terms. It is infrasonic, below 20 hertz, below the threshold of human hearing entirely. You cannot hear a blue whale song with your unaided ears, but you could feel it if you were close enough. Researchers have described feeling the vibrations through the hulls of their boats, through the soles of their feet, through the water itself. This song, if song is even the right word for something so low and so vast and so ancient, can travel in the right oceanographic conditions for more than 1,600 kilometers. There is a layer of the ocean, a band of depth, where temperature and pressure reach a particular equilibrium, where sound waves become trapped and travel horizontally with almost no loss of energy. It is called the SOFAR channel, the sound fixing and ranging channel, and whales have been using it for millions of years. A blue whale singing in the waters off the coast of Ireland can, in favorable conditions, be detected by a hydrophone placed in the waters off Virginia. The ocean does not merely carry the sound, it amplifies it. It becomes a cathedral of it. The blue whale song has been slowly deepening since the 1960s, a shift measured in careful acoustic records, the notes getting lower, decade by decade. No one is entirely sure why. Possibly it is connected to population recovery. As there are more whales in the ocean, individuals no longer need to call at the highest possible volume and can afford to relax into lower registers. Or possibly it is something we have not yet understood, some long, slow cultural shift drifting through the population, the way a musical trend drifts through a generation of human listeners. Humpback whales take this further still. Their songs, technically within the auditory range of a listening human, are long, structured, complex. They last for minutes, sometimes for hours. They are organized into phrases and themes that follow consistent patterns, the way a piece of music follows its own internal logic. And those songs change over time, new phrases spreading through populations the way a new melody spreads through a music scene, adopted and modified and passed along until a song heard today is almost unrecognizable from the one recorded decades ago. Humpbacks in one ocean basin sing differently from humpbacks in another, like regional dialects. New innovations appear, travel, and are absorbed. Whales have culture in a meaningful sense of the word. In the quietest part of the deep ocean, in the hours between midnight and dawn, when the surface ships are fewer and the ambient noise is lowest, the ocean fills with this sound, low, resonant, unhurried. Frequencies so deep they move through rock and sediment as well as water. Notes that take minutes to complete a single cycle. An animal that weighs 150 tons, drifting through the dark water, its great heart beating twice a minute, sending its voice out through the ocean's own acoustics to reach another animal that might be swimming right now, somewhere off a coastline on the other side of the world. This is where that wolf-sized animal wading into the warm shallows 50 million years ago was going. This is what that first tentative step into the water eventually became. The whole story, the bones, the slow migration of nostrils, the shrinking hind legs, the stretching vertebrae, the growing flippers, all of it pointed here to this dark water, to this slow heartbeat, to this vast and invisible song. Let your body go heavy, not all at once. Just let it happen on its own, the way the day always seems to loosen its grip when the room goes quiet and the light goes low. Feel the mattress beneath you. Feel the pillow holding the weight of your head. There is nowhere you need to be. There is nothing left to decide. Whatever was difficult today has already passed into the past, and the past cannot ask anything more of you tonight. Your breath is slower now. Good. Let it stay there. We are going somewhere extraordinary this evening. We are going down very gently, very slowly, into the sea. Not the cold, crashing kind of sea that the mind pictures when it braces itself, but the other kind, the still, dark, middle kind, where the water is neither warm nor cold, but simply there, holding everything suspended in a kind of glowing, unhurried quiet. We are going to a place where the rules about beginnings and endings are softer than you might expect, where something very small, smaller than the nail on your smallest finger, has found a way to start again whenever it needs to, where life discovered its own version of the reset. Breathe. You are already beginning to drift. Let the water come up around you. It is very gentle, and the story starts. Somewhere in the Mediterranean Sea, if you were to take a very small glass jar and dip it carefully into the shallows near a harbor wall, near the kind of wall where green weed clings to stone and the air smells of salt and old rope and the sea-damp wood of fishing boats, you might bring up, almost by accident, something so small you could easily mistake it for a speck of floating debris. It is not debris, it is alive. It is a jellyfish, but it is a jellyfish so small that its entire body could sit comfortably on the nail of your little finger and still leave room at the edges. Its name is Turritopsis dohrnii, and it was first described by scientists in 1883 in the waters near Naples, Italy, in that same warm and ancient Mediterranean light. For most of the following century, it lived in near total obscurity, studied occasionally, noticed rarely, filed away in taxonomy like thousands of other small marine animals whose lives go largely unremarked by the world above the waterline. And then in the 1990s, a pair of biology students named Christian Sommer and Giorgio Bavistrello were keeping a colony of these tiny jellyfish in a jar. They came back one day expecting to find the mature, free-swimming adults they had been tending, and found instead something that should not have been possible: newly settled polyps. The adults had not died. They had not reproduced in any normal sense. They had gone backward. They had returned to the very first stage of their lives, as if the body had pressed a button that no one, until that moment, had known existed. Picture it for a moment. Picture what this jellyfish looks like, so you can hold it in your mind. It is bell-shaped. Its body, the bell, is nearly transparent, the way very fine glass is transparent, or the way ice becomes transparent when the light hits it from exactly the right angle. You can see through it. You can see the deep red of its stomach, that small, vivid center, glowing like an ember in the middle of all that pale clarity. Around the rim of its bell hang white tentacles, up to 90 of them in adult specimens, each one fine as a thread, trailing through the water with a slow and patient grace. It pulses. That is the word for how it moves. Not swims, not flies, but pulses. The bell contracting and releasing in slow rhythmic compressions, each one gentle enough that the water barely notices. At 4.5 millimeters across at full maturity, Turritopsis dohrnii is smaller than a shirt button. The ocean it inhabits is millions of square kilometers wide. The contrast between those two things, the vastness of the sea and the tininess of this creature drifting through it, has a quality that is almost meditative if you let it settle in. Something this small, containing this much quiet mystery. It has been found now in waters far beyond the Mediterranean, in the Pacific, the Atlantic, the Gulf of Mexico, around Japan, along the coasts of Brazil and Panama, and the Indian River Lagoon in Florida. Marine biologists believe it has spread across the world's oceans by attaching to the hulls of ships or surviving in the ballast water that cargo vessels carry in their holds. A tiny, immortal stowaway, hitching slow rides around the entire planet. There are populations alive right now in the dark water beneath every major shipping lane. Now, this is where the story becomes something truly unusual. Like all jellyfish, Turritopsis dohrnii begins its life in a form that looks nothing like the creature it will become. It starts as a planula, a tiny, free-swimming larva, smaller still than the adult, covered in fine hairs called cilia that beat against the water as it drifts. The planula eventually settles. It attaches itself to a surface, a rock, the underside of a dock, the hull of a vessel, the flat darkness of the seafloor. There it becomes a polyp, a small anchored plant-like stalk, rooted in one place, extending short tentacles upward into the passing current, patient as a flower waiting for a bee. From the polyp, over days and weeks, small medusa bud off, the free-swimming bell-shaped adults. They detach. They drift upward into open water, pulsing, growing, following the slow drift of ocean currents in the shallow upper layers of the sea. They reach maturity. They reproduce. And then, in almost all jellyfish, that is the end of the story. The medusa ages and dissolves back into the water, and the cycle carries forward in its offspring. But in Turritopsis dohrnii, when the adult body is under stress, when it is damaged, when it is starving, when the water temperature shifts in a way that strains its systems, something different begins to happen. The jellyfish stops pulsing. Its tentacles retract, drawing slowly back toward the bell, one by one, like fingers curling. The bell itself contracts inward, softening, collapsing the elegant architecture of the adult form. The whole animal settles to the seafloor and folds into a small cyst-like mass, a quiet, unmoving blob of living tissue. It does not look like a jellyfish anymore. It does not look like much of anything. And inside that quiet mass, the most remarkable thing begins. The specialized cells of the adult body, cells that had been committed, locked in, designated for specific tasks, begin to change. A muscle cell, which had spent its whole existence as a muscle cell performing the contractions of the bell, suddenly stops being a muscle cell. It begins to transform into something else, a nerve cell perhaps, or a skin cell, or a reproductive cell. This process is called transdifferentiation, and it is extraordinarily rare. In almost all animals, once a cell has committed to a particular fate, that commitment is final. A liver cell stays a liver cell. A blood cell stays a blood cell. The molecular switches that determine cellular identity are not supposed to reverse. In Turritopsis dohrnii, they reverse completely, reliably. The specialized cells abandon their assignments, revert to something closer to a stem cell, an uncommitted, open state of potential. And then, following the instructions laid down in the creature's DNA, rebuild themselves into the cells needed for a younger body. Over 24 to 72 hours, the cyst reorganizes itself into a new polyp. The same animal, the same DNA, the same genetic individual, but young again, at the very beginning again, ready to grow back into an adult which can, if needed, reverse again. Japanese scientist Shin Kubota, based at Kyoto University's Seto Marine Biological Laboratory, has kept a colony of these jellyfish for decades, and over a 2-year period, he observed his colony undergoing this reversal 11 separate times. 11 rebirths, the same individual animals cycling. Kubota has spoken publicly and with obvious feeling about what he calls the deep lesson of this animal, that life does not have to move only in one direction, that biology contains possibilities we have barely begun to understand. It is important to say clearly, this is not true immortality in a practical sense. These small creatures are fragile. They are eaten by fish, by sea slugs, by crustaceans. A storm can destroy them. A sudden change in salinity can end them. The biological mechanism of reversal only operates in perfect laboratory conditions. In the open ocean, most individuals probably die of ordinary causes before they ever need to use it. The immortality of Turritopsis dohrnii is a potential, not a guarantee. A door that exists, that can be opened, but that most individuals never reach in time. What it is, though, is a proof of concept, a demonstration written in living chemistry that cellular identity is not as fixed as we assumed, that a body can, under the right conditions, say, "This chapter is over. Let us begin again." Now let yourself drift a little further into this image. The Mediterranean at night, somewhere between the surface light and the dark of the lower water, at a depth where the sun's last blue-green rays dissolve into a gradual dimness. There is a quality to that light, or to that absence of light, that is very difficult to describe to someone who has never been in it. It is not the darkness of a room with the curtains drawn. It is more like the darkness of very early morning, before dawn has fully committed, when the sky holds a faint ambient glow that has no clear source. Blue, quiet, soft-edged. In that water, something is pulsing. The bell opens, a slow outward expansion, the transparent walls pressing against the water, then the gentle recoil, the contracting inward, open, close, open, close. The white tentacles trail behind and beneath, stirred slightly by each pulse into slow, wavering patterns. The red stomach at the center glows faintly, that ember of color suspended in all that translucency like something very small and very warm held carefully inside cupped hands. There is no brain inside this creature, no nervous system in any sense that corresponds to experience as we know it. There is no fear in the drift, no awareness of the dark, no calculation of direction. There is only the pulse, the current, the water moving through the tentacles, the slow chemistry of living. It is a kind of peace that exists entirely without effort, entirely without decision. The ocean simply carries it, and it goes. And when the cold comes, or the hunger comes, or the damage comes, when something in the body's chemistry says, This cannot continue. The retreat begins. Slow, patient, the tentacles folding inward, the bell softening, the whole animal settling gently to the surface of a rock on the seafloor where the water is still and the current does not reach, becoming small, becoming quiet, and then in that stillness, the long and extraordinary work of beginning again. There is something in that image, the deliberate folding inward, the choosing of stillness as the prerequisite for renewal, that feels, if you let it, like something you recognize, not in a scientific sense, just in the sense that the body you're lying in right now is also, in its own way, beginning its nightly reset. This is something researchers have understood in increasing detail over recent decades. While you sleep, really sleep, the deep, slow wave kind where the brain settles into its longest, quietest rhythms, your hippocampus, the part of your brain most involved in forming and holding memories, undergoes a process called consolidation. The experiences of the day, encoded in unstable patterns of neural firing, are replayed, strengthened, and woven carefully into longer-term storage. What was raw is refined. What was fragile is made durable. And then, in a discovery published just in 2024 in the journal Science, researchers at Cornell University found something more, that at certain moments during deep sleep, specific regions of the hippocampus go completely silent. The neurons that had been firing all day, learning, encoding, responding, simply pause. In that silence, they reset. They become available again, ready to receive new information when morning comes, as though the slate has been gently, carefully cleared. The same neurons, renewed, ready to be used again. A reset, written in the language of brain chemistry, just as the jellyfish's reset is written in the language of cellular biology. Both require the same precondition: stillness, withdrawal, the folding inward. When Turritopsis dohrnii pulls its tentacles close and settles to the seafloor, it is not given up. It is doing the most sophisticated thing it knows how to do. It is creating the conditions under which renewal becomes possible. And when you lie here in the dark, you're breathing slower now, your thoughts losing their daytime architecture and beginning to drift at the edges, you're doing something structurally similar. You're withdrawing from the active, outward-facing mode of the day. You're giving the body and brain the stillness they need to reorganize, to consolidate, to repair, to reset. There is a small, translucent creature somewhere in the Mediterranean Sea right now, pulsing slowly in the dark water, its red center glowing faintly. It does not know it is remarkable. It does not know that biologists travel from across the world to study what it does quietly and automatically, in the warm shallows, with no particular effort, as an ordinary fact of being what it is. It simply drifts. And when it needs to, it begins again. You are allowed to do the same. The day is already behind you. What happened in it belongs to the day, and the day is finished. The neurons are quieting. Somewhere in the dark sea of the body, a slow pulse. The tentacles folding, the bells settling, the long, patient work of beginning again, carried out in silence in the dark, without any effort on your part at all. Let the water hold you. Let yourself drift now a little further out. There is nothing left to do but rest. There is an animal out there in the blue-black water right now. It is resting on a shelf of pale rock. its body spread softly against the stone like a poured liquid, finding its shape. 8 arms trail away from it in loose, unhurried arcs. Its skin, at rest, is the dusty amber color of old parchment. But watch it. Watch it for just another moment, because any second now, without any apparent effort, without any visible movement of intention, the whole surface of its skin is going to become something else entirely, something that has never existed before and will never exist again, shaped in this exact way, for this exact rock, on this exact patch of seafloor, at this particular hour of the night. This is the octopus. And its story begins, as the best ones do, 500 million years before it looked anything like this. Imagine the ocean as it was 530 million years ago. There are no whales, no fish with jaws, no coral reefs, no familiar architecture at all. The sea is an older, stranger thing than anything we would recognize. Shallow and wide across most of the planet, lit from above by a younger, slightly dimmer sun. The floor of it is soft and brown with silt, and moving across that silt in the warm shallows of the early Cambrian are creatures encased in shell. Coiled shell, straight shell, conical shell. The ocean floor during this age is a workshop of calcium carbonate architecture, every living thing wearing its house on the outside. This is where the cephalopods begin. Not as octopuses, not as anything fluid or dramatic or quicksilver, but as small shelled mollusks hugging the bottom, creatures that would not look to a modern eye entirely different from a snail. Their earliest confirmed ancestor in the fossil record is something called Plectronopterus, found in the late Cambrian. And what distinguishes it from an ordinary mollusk, what sends it off down a different evolutionary corridor, is a small and elegant structure inside its shell, the siphuncle. This is a thin tube of tissue that runs through the shell's interior chambers and allows the animal to pump gas in and out of them, adjusting the shell's buoyancy the way a submarine adjusts its ballast. That small tube changed everything. It meant the shell could float. And an animal that could float was no longer tied to the seafloor, no longer shuffling through silt. It could rise. It could move through open water. The ocean, which had previously been an obstacle above them, was suddenly a space to occupy. Over the next 100 million years or so, the cephalopods, now carrying that buoyancy trick in their lineage, radiated into the seas with the kind of confidence that comes from having found something that works. The nautiloids appeared, and they grew large and extraordinarily varied, some with tightly coiled shells, some with long, straight, conical ones, some stretching to 2.5 meters in length, drifting through Ordovician waters like elegant spears. They became predators in an age when the ocean had very little else worth calling a predator. For a long time, they were the most formidable things in the sea. Then the ammonoids arrived, a related lineage that kept its external shell but developed those extraordinary, intricate suture patterns along the interior walls, geometric and precise as stained glass, which you can see still if you find an ammonite fossil and look closely at the swirling seams across the surface. The ammonites spread across every ocean, survived extinction after extinction, and left behind so many fossils that they appear today on the shelves of curiosity shops all over the world. Those flat stone spirals worn smooth by time and the hands of collectors, holding something of that ancient ocean in their geometry. But within the nautiloid group, another branching was already quietly underway, a lineage called the coleoids. The group from which octopuses, squid, and cuttlefish would eventually emerge began doing something remarkable with the shell. They did not simply refine it, or coil it differently, or build more elaborate chambers into it. They began to move it. The shell, that original inheritance from the Cambrian, that external house of calcium and hard geometry, began to migrate inward. At first it became smaller, tucked beneath the mantle of skin and muscle, a structural remnant rather than a suit of armor. Then smaller still, and eventually, for the branch that would become octopuses, it disappeared almost entirely. What remains today in most octopus species are two tiny vestigial structures called stylets. Small spike-like remnants of the old shell machinery hidden deep inside the body, like the memory of something the lineage is no longer quite sure it needs. The primary trend in coleoid evolution, as one lineage of researchers has put it, was the internalization and eventual loss of the shell. And that loss, counterintuitively, was one of the great liberating events in the history of animal life. Without the shell in the way, without that rigid gas-filled structure setting hard limits on depth and flexibility and shape, the animal was free to go deeper than any shelled cephalopod could follow. It was free to change shape, to compress itself through any opening larger than its own beak, to flow rather than drift. The ocean's greatest depths became accessible, and the body, freed from its armor, was suddenly available for other things, for softness, for sensitivity, for the kind of skin that can do what no other skin in the history of life has ever done. The octopus brain is difficult to describe in the terms we ordinarily use for brains. We tend to think of brains as centralized things, a single organ housed safely in the skull that receives information from the body, processes it, and sends instructions back out. The body is the messenger. The brain is the seat of the mind. That arrangement works perfectly well for us, and for dogs, and for fish, and for most of the animals we are likely to think about before sleep. But for the octopus, that arrangement would be a catastrophic waste. Consider the problem the octopus faces. It has 8 arms, each of which can extend, contract, twist, grip, taste, smell, and feel, completely independently of one another and completely independently of any fixed skeleton or rigid geometry. An arm can curl into a tight spiral or stretch out flat and straight. It can reach into a crevice while the other 7 arms are doing 7 entirely different things. The arm has no bones to report its position back to the brain the way a human limb does. It exists in a state of essentially infinite possible configurations. If every movement of every sucker on every arm had to be cleared with a central brain first, the octopus would be paralyzed by its own complexity. So, evolution found a different answer. The octopus has around 500 million neurons in its body, a number comparable, remarkably, to a dog. But the arrangement of those neurons is unlike anything else in the animal kingdom. Only about 1/3 of them live in the central brain, the donut-shaped mass of neural tissue tucked between the animal's eyes, a brain so compact, incidentally, that the esophagus runs straight through the middle of it, meaning that when an octopus swallows food, The food literally passes through the center of its own thinking. The remaining 2/3 of those 500 million neurons are distributed throughout the arms themselves, roughly 40 million neurons per arm, organized into dense clusters called ganglia that run the full length of each limb like a second spine. Each arm has its own local intelligence. It can gather sensory information from its 2,000 or so suckers, each sucker containing approximately 10,000 neurons of its own, capable of detecting touch, texture, pressure, and chemical signals simultaneously, process that information locally, and issue its own movement commands without waiting for authorization from the central brain. Researchers have demonstrated this by severing an octopus arm and applying a small electrical stimulus to it. The detached arm responds with the same coordinated, biologically appropriate movements it would have made while still attached. The arm does not know it is detached. It simply continues being what it is, a semi-autonomous agent moving through the world with local purpose. What the central brain does is something higher and more abstract. It sets the overall agenda. When an octopus decides to investigate a crevice in search of a crab, the central brain broadcasts something like a general directive, and each arm receives that directive and works out independently how best to carry its own contribution to it. The arms report useful sensory information back to the brain. The texture of the wall they are touching, the chemical signature of a nearby food source. But they do not wait for the brain to tell them how to move their suckers. They have already figured that out themselves. There is, to our human intuitions, something almost vertiginous about this. We think of consciousness as a thing that lives in one place. We imagine that there is a self sitting somewhere behind the eyes, managing the rest. But the octopus suggests that this may be one way of doing things, not the only way. Its mind is liquid in the sense that its body is liquid, spread through the whole, reaching outward, thinking at the periphery. 8 arms moving through the world with a degree of independent purpose, coordinated by a central intelligence but not entirely beholden to it, suggesting a form of awareness that is distributed across the body the way a conversation is distributed across the people having it. The central brain of the octopus, it is worth noting, has a brain-to-body ratio larger than most vertebrates, a measurement that scientists use as a rough proxy for cognitive complexity. The octopus's optic lobes alone, the large paired structures that process visual information, contain between 120 and 180 million neurons. For comparison, the entire brain of a common frog contains around 16 million neurons. The octopus's eyes are processing more information with more dedicated neural machinery than the entirety of a frog's cognition. And those eyes are, in the estimation of most biologists, among the most sophisticated in the invertebrate world, camera-like, with a lens, an iris, a pupil, and a closed cornea that no other cephalopod possesses. They evolved this complexity entirely independently from the vertebrate eye, arriving at a nearly identical solution through an entirely different evolutionary path. And now we come to the strangest part, the part that is hardest to hold in the imagination and therefore the most worth trying to hold. The skin of an octopus is not a boundary. It is not the place where the animal ends and the world begins, the way skin works for most of us. It is, instead, a living instrument of extraordinary complexity, a surface that reads the world, translates that reading into pattern and texture and color, and broadcasts those translations back at the world in real time in less than a second, faster than any conscious decision could account for. Spread across the surface of that skin are millions of structures called chromatophores. Each one is a tiny sac filled with nanoparticles of pigment, yellow or red-brown or near black, depending on its type, surrounded by an elastic membrane, which is itself ringed by small radial muscles spreading outward like the spokes of a wheel. When those muscles contract, they pull the membrane outward, stretching the pigment sac into a flat disc of visible color. When they relax, the sac contracts back into near invisibility, smaller than the width of a human hair. Each chromatophore is under direct neural control. A single nerve signal tells each one whether to open or close, and on the skin of a single octopus, this is happening in millions of places simultaneously, every fraction of a second, in patterns of astonishing resolution. More chromatophores per square inch, researchers have noted, than any other cephalopod, producing images on the body's surface with a fineness of detail that has been compared to a high-resolution display. Beneath the chromatophores lie iridophores, cells filled with stacks of thin, light-refracting plates that produce iridescent blues, green, silver, and gold, shifting their apparent color depending on the angle from which they are viewed, like the surface of a soap bubble or the inside of an abalone shell. Below those are leucophores, cells that scatter light across the full visible spectrum and appear white, providing a bright backdrop against which the chromatophores can produce the high contrast patterns needed for disruptive camouflage, the kind that breaks up the outline of the body so effectively that a motionless octopus pressed against a rock simply ceases to read as a three-dimensional object in the minds of the predators scanning the area for prey-shaped things. But color alone is not enough to disappear. The ocean floor is not a flat, smooth canvas. It is rough, granular, encrusted with barnacles and coralline algae and the irregular geometry of worn stone. A smooth-skinned animal lying against it would still be visible by its outline, by the flatness of its surface against the rough three-dimensionality of the background. So the octopus has a solution for that too. Distributed across the skin are structures called papillae, small, muscular projections that can be raised or flattened under neural control, changing the three-dimensional texture of the skin surface from smooth as still water to rough as an encrusted reef wall, to spiked and irregular as a tangle of algae, all within fractions of a second. Think of the most complete voluntary control over every individual goosebump. But instead of goosebumps raised by a cold, these are precise sculptural elements, each one shaped and positioned to replicate the exact texture of whatever surface the octopus is pressing against. Researchers have compared the octopus skin to a muscular hydrostat, the same principle that controls the human tongue, and found that the papillae can produce textures ranging from small rounded bumps to tall pointed spines to broad flat ridges, depending on which muscles in the hydrostat contract and which relax. What makes this stranger still is a discovery made in the last decade or so. The skin of an octopus is, to some degree, light sensitive in its own right. researchers found that the same light-detecting proteins, opsins, the molecules that enable vision in the eyes, are present in the sensory neurons scattered across the skin surface. When light falls on isolated octopus skin, kept alive in a laboratory dish, the chromatophores respond. They expand and change color without any input from the brain or the eyes. The skin, cut off from everything else, is still doing something that resembles seeing, not detailed, image-forming vision. Researchers note that this dermal light sense detects changes in brightness rather than patterns of contrast, but awareness nonetheless. The skin is aware of the light falling on it. It can respond to that light directly. What this suggests, though scientists are careful about the language they use for it, is that the octopus does not only camouflage from the outside in, seeing the environment with its eyes and then directing its skin to imitate it. Some part of the camouflage may involve the skin reading the light environment directly and making its own adjustments, the way a leaf adjusts its chlorophyll production in response to the light reaching it, except that in the octopus, this process happens in milliseconds and produces patterns of staggering complexity. The body thinks for itself in ways the central brain may not even be fully aware of. The result? The reason all of this is worth the 50 seconds a predator might spend scanning the reef before moving on is that an octopus at rest on a textured surface becomes, for all practical purposes, that surface. The patterns on its skin replicate the color distribution of the rock or coral beneath it. The papillae raise and shape themselves to match the three-dimensional profile of the background. The leucophores provide the correct whites. The iridophores provide the shimmer of wet stone in filtered light. And if you were swimming above it, looking down, you would see the sea floor. You would not see the animal. The animal would be right there, pressing itself into the stone, 8 minds worth of thinking distributed through 8 arms, all of them quietly, almost meditatively still, while the skin around them played its slow, elaborate act of becoming something else. Octopuses are tool users. They have been filmed carrying coconut shell halves across open stretches of sand, not using them immediately, but holding them in reserve, navigating awkwardly with the shells tucked beneath them, making themselves more visible and more ungainly in the short term in exchange for a shelter they will need later. This kind of planning, carrying an object for future use, suffering a present disadvantage for a future benefit, requires a model of time that extends beyond the immediate moment. It requires something like foresight. Among invertebrates, tool use of this complexity has been recorded in exactly one group: octopuses and their close cephalopod relatives. They recognize human faces. Researchers at a New Zealand university found that a captive octopus took a consistent dislike to one particular staff member, squirting water at her whenever she passed a tank, while behaving neutrally around others. The ability to distinguish individual faces across species, to tell one human from another, implies a level of social and cognitive processing that we tend, almost reflexively, to reserve for mammals and birds. Octopuses do not read those categories. They simply have the brain they have and use it the way it works. They have been known to escape their tanks, cross the floor of aquarium facilities in the dark, enter adjacent tanks to feed, and return to their own tanks before morning. They open jars. They solve mazes. They are, as one neuroscientist at Stanford put it, a brain that evolved essentially from something like a slug, arriving at intelligence that is functionally comparable to that of a dog, but along an evolutionary path that diverged from the vertebrate lineage roughly 550 million years ago, sharing virtually no common neural architecture with us, building its cognition from completely different materials. And then there is what happens when they sleep. A 2023 study published in the journal Nature observed octopuses during sleep and found something unexpected and rather wonderful. About once an hour, a sleeping octopus would transition from a state of quiet rest, motionless pale skin, eyes narrowed to slits, into a brief, vivid burst of what researchers described as active sleep. During these episodes, which lasted typically from a few seconds to about a minute, the octopus's brain activity shifted to closely resemble the neural patterns recorded when the animal was awake and active. Its arms twitched, its breathing quickened, and its skin, that remarkable living surface, began to move through colors and textures and patterns in rapid, unpredictable sequence, as if the animal were running through some compressed private library of its waking experiences. Sleep spindle-like waveforms resembling the neural signatures seen during a non-REM sleep in mammals were identified in the octopus brain regions associated with learning and memory, suggesting they may serve a similar function to our own slow-wave sleep, the consolidation of what the day has taught. And an active sleep phase bears a striking resemblance to REM sleep, the phase during which, in human brains, the most vivid dreaming occurs. The scientists are careful not to claim more than the evidence supports. An octopus cannot tell us what it experiences during sleep, and the science of invertebrate sleep is still finding its footing. But if octopuses do dream, and the researchers note that if they do, the brevity of their active sleep phase suggests something closer to a brief, vivid flash than to the elaborate narrative arcs our own dreams construct. Then the content of those dreams is written in color and texture on the surface of the body, available to be watched. The skin flickering through its patterns in the dark of some quiet tank or some dark shelf of reef is a visual diary of the mind asleep. Somewhere out there right now in the deep blue expanse of an ocean you may never visit, a turtle is moving through the dark water slowly, deliberately, with a kind of patient grace that humans can only admire from a distance. Its shell is smooth and flattened, not the dome of a land tortoise, but something more suited to gliding, something shaped by millions of years of water pressing gently against it, nudging it toward a more perfect form. Its front flippers rise and fall in a rhythm that looks, to those who have been lucky enough to watch it underwater, almost exactly like wings. The turtle doesn't hurry. It has never needed to. The ocean is enormous, and the turtle has all the time in the world. Sea turtles are among the oldest living animals on Earth. Their lineage traces back at least 220 million years, to a time before the continents had fully separated, when the world's land masses were still pressed together in a single vast supercontinent. Back then, a distant ancestor, a creature called Odontochelys, roughly 40 centimeters long, with only a half-formed shell and a mouthful of actual teeth, was already venturing into shallow seas. Scientists believe it may have been the first turtle to leave the land behind. By the time the dinosaurs were at their peak, sea turtles were already ancient. They swam through warm Cretaceous seas alongside creatures whose names read like something from a fever dream. Mosasaurs, plesiosaurs, ammonites, as wide across as dining tables. Some prehistoric sea turtles grew to spectacular sizes. Archelon, which lived around 75 million years ago in what is now North America, measured nearly 5 meters from the tip of its beak to the end of its tail and weighed around 2,200 kilograms. It was, in every sense, a giant of the ancient ocean. And then the asteroid hit. Roughly 66 million years ago, a mass extinction event wiped out 3/4 of all life on Earth. The dinosaurs disappeared. Countless other lineages were simply erased. But the sea turtles survived. No animal heavier than about 25 kilograms made it through, except for sea turtles and crocodiles. Something about their biology, their patience, their ancient relationship with the sea allowed them to endure what nothing else could. Today, 7 species of sea turtles still swim the world's oceans. The loggerhead, the green, the hawksbill, the leatherback, the flatback, the olive ridley, and the Kemp's ridley. They live in tropical and subtropical seas, in warm coastal shallows and the open deep ocean. And they are all, to varying degrees, endangered. But they are here, still here, moving through the dark water as they always have. There is something deeply calming about that. Something worth sitting with for a moment before we go any further. Now let us consider something that the sea turtle carries with it everywhere it goes. Something invisible, weightless, and extraordinary. Something no scientist fully understood until quite recently. The Earth has a magnetic field. You probably learned this somewhere along the way. It's what makes compass needles point north, what shapes the shimmering curtains of the aurora borealis near the poles. The field emanates from deep within the planet's iron core, bowing outward and wrapping around the globe like the skin of a great invisible fruit. It is not uniform. It varies in intensity. In some places, it is stronger, in others, weaker. It also varies in inclination angle, the angle at which the invisible field lines tilt as they intersect the Earth's surface. Near the poles, the lines dip steeply. Near the equator, they run nearly horizontal. Every geographic location on the planet has its own unique combination of these two qualities, its own magnetic signature, like a fingerprint pressed into the invisible fabric of the world. Sea turtles can read those fingerprints. They have evolved not one but 2 distinct magnetic senses, which researchers at the University of North Carolina at Chapel Hill have spent decades slowly, carefully teasing apart. The first sense functions like a compass. It tells the turtle which direction it is heading. The second sense functions like a map. It tells the turtle where it is. Together, they give sea turtles something functionally close to a global positioning system, one that requires no satellites, no batteries, no signal, just a quiet, biological attunement to the invisible geometry of the planet itself. How this works at the biological level is still not entirely settled science. Researchers believe that the map sense relies on something like a touch-based perception of magnetic forces, a sensitivity that can actually be disrupted by a brief magnetic pulse. the same way a compass needle can be temporarily thrown off. A 2025 study published in the Journal of Experimental Biology showed that when hatchling loggerheads were exposed to such a pulse, they stopped responding to magnetic fields they had previously learned to recognize. The sense was temporarily scrambled, and with it, the ability to read location. The compass sense, on the other hand, appears to involve something different, possibly a mechanism that allows the turtles to perceive the direction of magnetic field lines through something closer to vision, a subtle awareness of light and orientation that most animals don't possess. The details are still emerging, but what we know clearly is this: sea turtles are born already carrying something remarkable inside them. From the very first moment they enter the sea, they are already reading the world through a sense that most creatures, including us, will never know. Let's go back to the beginning, to a beach at night. The sand is warm, faintly luminescent, where the moonlight catches the wet grains at the waterline. Above, the stars are extraordinary, dense and white and numberless, reflected dimly in the dark surface of the sea. Nothing moves on the beach. The dunes are still. The waves arrive in long, slow exhales, each one pulling back with a soft, retreating hiss before the next comes rolling in. Then the sand begins to stir. Somewhere above the waterline, about 40 centimeters below the surface, there is movement. A tiny flipper pushes through the dark. Then another. Then a head, small, dark, with eyes that are already open and already searching. A loggerhead hatchling claws its way upward through the packed sand, breaking through into the night air for the very first time. Within minutes, dozens more are doing the same. The nest erupts. Small dark shapes scramble across the pale sand, moving with surprising speed toward the luminous shimmer of the ocean. They are guided first by light. The sea reflects the sky and is always the brightest thing on the horizon, but they are guided too by the planet itself. Even before they reach the water, they are already reading the magnetic field. Once in the surf, a hatchling enters what researchers call the frenzy period. For the first 24 to 36 hours of its life, it swims almost without stopping, driving itself offshore, away from the shallow coastal waters where predatory birds and fish gather in abundance. It can feel the orbital movement of the waves, the way each swell rolls through the water like a slowly turning wheel, and it aligns itself against them, using that rolling motion as a guide to maintain a heading directly out to sea. The destination is the Gulf Stream, a great river of warm water that sweeps northward along the coast of the southeastern United States before curving east across the Atlantic. The hatchling does not know the name of this current. It does not know what a map is, but it knows, through something older and quieter than knowledge, which way to go. When it encounters a magnetic field characteristic of the edge of the warm current system, something in its nervous system responds. It adjusts course. It keeps swimming. The North Atlantic gyre is the larger system the Gulf Stream feeds into, a vast circular current that flows clockwise around the Sargasso Sea, carrying warm water from North America across to Europe and Africa and back again. For a young loggerhead, staying inside this gyre is a matter of life and death. Stray north of its boundary into the cold waters off Scandinavia or the British Isles, and the turtle will cool and slow and die, drift south into the current systems below the equator, and it may be carried far from its range into waters it cannot survive. The gyre is a cradle. The turtle must stay inside it, and so the hatchling swims out into the open Atlantic on its own, the size of your palm, weighing about half an ounce, navigating by a sense we are only beginning to understand. The years that follow have long been called the lost years. From the moment a hatchling disappears over the horizon until it reappears years later as a juvenile large enough to be seen from a boat, scientists could not say with certainty where it went. The ocean is enormous. The turtle was tiny. Tracking technology took decades to catch up. We know now that young loggerheads from Florida's Atlantic coast spend somewhere between 6 and 12 years circling the North Atlantic gyre. They ride the Gulf Stream north and east, crossing to the other side of the Atlantic, visiting the waters off the Azores and the Canary Islands and the coast of Portugal. Some spend time in the calm, seaweed-carpeted expanse of the Sargasso Sea itself, where mats of floating sargassum provide shelter and food. Then, eventually, they begin to find their way back west, growing all the while, maturing slowly, accumulating something that functions like experience. What guides them through all of this is their magnetic map. Research has revealed that loggerhead hatchlings, when exposed in laboratory conditions to the magnetic fields that exist at specific locations along their migratory route, respond by swimming in the direction that would, if they were actually at that location, keep them on course. Exposed to a field replicating the northern edge of the gyre near Portugal, they swim southward. Exposed to a field matching the western Atlantic, they swim northeast. They have never been to these places. They have never migrated before. And yet they know, with something quieter and deeper than conscious thought, what to do. The turtle does not experience this, we can only assume, the way you or I might experience looking at a map and plotting a route. There is no deliberation, no decision-making in the human sense. There is only movement. The slow, wide arc of a flipper through dark water, the patient body drifting forward, the almost imperceptible tilt of a head as some invisible quality of the world around it shifts. Think about that for a moment. Imagine being so perfectly calibrated to the planet you live on that the planet itself becomes your guide. That the very field threading invisibly through every rock and ocean and grain of sand on Earth is something you can feel, the way you feel warmth or pressure or the texture of something held in your hands. The turtle carries no technology. It needs none. It is the technology. Researchers have found that turtles can detect both the intensity and the inclination angle of the Earth's magnetic field. Two independent measures that, taken together, uniquely identify almost any location on the globe. It is the equivalent of knowing your latitude and longitude without any instrument at all. In a 2025 study in the journal Nature, researchers at the University of North Carolina confirmed that loggerheads can not only read these magnetic signatures, but actively learn and remember them, storing the magnetic character of important places the way we might store a familiar address, retrievable even 4 months later. The slow beat of the turtle's flippers carries it forward through black water, through years, through the invisible magnetic geometry of the ocean. It is not in a hurry. It has never been in a hurry. It simply continues, one stroke and then the next. Somewhere between 20 and 30 years after that first desperate scramble across the sand, a female loggerhead becomes ready to nest for the first time. By now, she is large, a meter or more in length, perhaps 135 kilograms. She has survived things that killed most of her siblings in those first days. She has crossed an ocean and returned. She has grown, and now something pulls her back toward a coastline she has not seen since she was the size of a human hand. She doesn't navigate by smell alone, though she may use olfactory cues once she draws close. She doesn't navigate by following older turtles. She has no colony, no flock. She navigates overwhelmingly by the same invisible sense that has guided her entire life. She seeks a specific magnetic signature, one that she imprinted on in those first hours of her life, as a hatchling crossing from the warm sand into the cold surf. The combination of inclination and intensity that existed at that precise stretch of coastline has been stored inside her, like a memory so deep it has become instinct. Scientists confirm this in a remarkable long-term study. Over 19 years, they tracked where loggerhead females nested along the Florida coast and cross-referenced those locations with subtle shifts in the Earth's magnetic field. The Earth's field isn't static. It drifts slowly over decades, and the nesting locations shifted with it. When magnetic isolines, the invisible contour lines of equal field intensity, converged on a stretch of beach, more turtles nested there. When they spread apart, nesting density decreased. The turtles were not returning to a GPS coordinate. They were returning to a magnetic sensation, a feeling perhaps that no human word adequately describes. A famous loggerhead nicknamed Big Bertha was first tagged by researchers in 1980 and was still documented nesting in 2016. Genetic testing revealed she had daughters already nesting themselves, daughters who were between 30 and 35 years old, which would make Big Bertha somewhere between 85 and 91 years old. She had been navigating by the Earth's magnetic field, alone, for nearly a century. The female who arrives on tonight's beach does so quietly, in the dark, at high tide. She hauls herself up the sand with slow, immense effort. On land, she is clumsy, gravity unkind to a body built for water. She finds a place above the high tide line and begins to dig, using her hind flippers with a methodical, almost meditative patience. She digs a flask-shaped chamber in the warm sand and deposits her eggs, perhaps 100 of them, pale and round and leathery. And then she covers them and rests for a moment in the darkness, her breathing slow and audible, her eyes sealed against the dry air. And then she turns back toward the sea. The ocean is dark and enormous in front of her. The waves are arriving in their slow, steady rhythm. She moves into the surf and is lifted by it, and immediately she is transformed, the heaviness of her body dissolving in the buoyancy of the salt water, every movement becoming effortless again. Her flippers spread wide. She descends. The world above the surface recedes, the sound of the waves fades. There is only the deep, quiet pressure of the water and the invisible field of the earth threading through it, and the slow, ancient rhythm of a body that has been doing this for longer than most of the mountains on the land have existed. She is not thinking about any of this in the way we think. She is simply moving simply following something so deeply embedded in her biology that it cannot be separated from what she is. The ocean closes over her, and she is gone. And maybe that's a good place to let yourself drift too. There is something quietly reassuring about a creature that has been reading the invisible architecture of this planet for 220 million years, long before us, and very possibly long after. The earth hums with magnetic lines you'll never feel. Somewhere out there in the dark water, something is following them home. If this story helped you settle into sleep, a like or a subscribe to Pillow Trace means the world. It helps more people find their way here when the night feels long. Sleep well.